Right, let's do another problem. So today we're working on number 22, the last one in our week 2, in our 22-week, 7 hours per week schedule. And this one is diameter of a binary tree. So let's get started on that. Given the root of a binary tree, return the diameter of the tree. A diameter is the length of the longest path between any two nodes in a tree. The path may or may not pass through the root. How would it not pass through the... Oh, I guess if you just have like a something like this and then like you just have like a long path here instead. Interesting. Hmm. This kind of makes me want to do a sort of pre-order traversal type of thing, where we go all the way to the left, or try to go as far to the left as possible on one end. And a post order traversal towards the right. So this will go all the way to the right, then it'll go up, then it'll go left, right? So, and then the diameter can be calculated when we do the appropriate moves. So this would be left on pre-order and right on post-order. And subtract when we go back up or opposite, and also terminate when they meet. Because they're both traversing, I assume that they will terminate at some point. They will both meet at some point within the middle of the tree, or somewhere. Let's see. 3 is the length of the path 4, 2, 1, 3. So if we start from here and we do a pre-order, or we do a post-order traversal here, then we do a pre-order traversal here, okay, so we can't move them in sync because otherwise then the next step for this post-order traversal would be go back to the 1, which is what we don't want. But the pre-order can keep going to the 4. So then it would be, so here it would be 1, the path would be length 1, length 2, length 3, the problem is that if there's something nested here, how do we sort of calculate that? And this is a binary tree, not a binary search tree, so there's no sort of invariant there in order to so that we know that we're on the rightmost or the leftmost. We could go by depth, right? I think we can go also by depth. Most and rightmost by depth. So what I mean by that is that when we go to this depth right here, we know that, no. We do pre-order. Let's say going to the right is 1. So 0, -1, 1. So these two are considered equivalent in that case. So I'm thinking about when we go up or when we go left in our post order, that counts as a -1. But that doesn't make sense because then these two would be considered equivalent. And then we want to go 1, 2. Of course, this will be the maximum for our pre-order. So this will be 0, 1, -1, 0. Okay, no. Okay, yeah. So actually, I think my first solution will just be do a pre-order and then a full post order. Keep the node with the highest score, which is okay. I'll think about that in a bit. Keep the node with the highest score. So we said left on pre-order, right on post-order. Everything else is a -1. But the next question is, how do we calculate the diameter? So let's say that we have a 1 here, because this is root starts at 0. 1, -1, 0, -2. So we keep the 3. Then we have 1, 2. So we have a 2 here and a 1 here. And then we just add them? Let's give that a shot and let's see where we go from there. So let's see. We'll need to keep a reference to the node that we want on the leftmost. Our rightmost tree node. Compiler might actually yell at me because this is of type tree node question marks unnullable. But the number of nodes in the range is 1, 2. Okay. So technically there could be an edge case here, and a problem that I'd ask about is if the root could be null. In this LeetCode problem, they say that the number of nodes is in the range of 1 and 10 to the 4 inclusive. So that means that there's always going to be a root node. So I'm going to add double bang operator here. Some people say that this is a code smell, and I'm inclined to agree. But in this case, we know that within the context of this particular problem, that there will always be a root node, so I'm not worried about that. And actually, we don't need to keep a reference to the node itself. We only need to keep a reference to the value. We don't need to keep a reference to the values. We only care about the sort of score that it has. And technically, we could write this as a pre-order and a post-order sort of function that returns this score. And I'm gonna go ahead and do that just to make the code look a little bit cleaner. Root tree node, and this will return an int as well. And this int will be the score, the leftmost node. And we could just copy and paste that. So now we have a pre-order and a post-order, and now you get to watch me fail at implementing post-order and pre-order traversal. I mean, this is nice practice regardless, but okay, so we can say root is null 0. Hopefully the compiler is smart enough. And we can say val or var current node is root. Left score plus plus. And actually, no. Am I gonna need a queue or a stack for this? Or we can implement it in a recursive manner. We could do that. Implementing it recursively will use a little bit extra headroom, but I think it'll look nicer. So traverse left. So we can say pre-order current node left. And we can say left score plus equals, and then minus minus for the current node right is not null. Left score minus equals pre-order current node dot right. Let's see. And I'm gonna do something unconventional here and actually print this out to see what we get. Um, and we can add some prints here, so we can say print line, adding 1 for print node left, moving 1 for u, 1 for the right. And I just hope that I don't run into an NPE or something. Oh, right. Let's just return 0 here. Am I gonna TLE? Okay, so I guess I have a TLE issue here. I need to add this part. So it looks like we added 1 for 2 and then 4. I don't think we actually want to remove the left score here. Let's see. And I think I want to change these from whiles to ifs. And let's see what we get here now. Okay, we add 1 for 2, add 1 for 4, removed 1 for 4, removed 1 for 2, removed 1 for 5, and then remove 1. Okay, so yeah, this part is let's see where we're at for each one of these. We added 1 for 2, added 1 for 4. Then this was the first return and it returned 0? That doesn't seem to make sense. Added 1 for 2, added 1 for 4. Okay. Right. it's just interesting. Let's do this, +1. So that doesn't change anything there. Our right score. I think there's a max function. Let's see. Not text, not sequences. Math. Okay. So we can do that. Right score. Let's print the right score as well. Let me see where this leaves us. Zero, 1, and 2. Right, because here we have 0 and 0 for the left and the right. Here we have 1 and -1 for the left and the right. Then here we have 2 and -1 for the left and the right. So I think this is what we want, because this is operating in a recursive manner. Technically I could put these into its own line. Do I need to import Kotlin math? Import Kotlin math dot max. Okay. So now we just sort of need to do the same exact thing, but for the right side. But now we do minus, plus. Oh, we actually want to do that. Post order root. Print line rightmost. Leftmost. Most. So this ends up doing 2 traversals, which probably isn't the most optimal. You could probably find a way to do this with just 1. Let's see. But I think it does make sense. we always want to keep the right score. Or sorry, we always, when we go left, we want to add 1. When we go right, we want to subtract 1. And then we always want to keep the max of whatever is there. So in a case of this, and then we add the results of the leftmost and the rightmost scores. And even if we have a case like 1, 2, 4, 5, null, null, 4. Now we want null, null, 3, null, 3. So technically the diameter here is, let's see, 0, 1, 2, 1, 0, 1, 2. Let's do some funky thing. Null 5. And let's make this different, so 6. 6 and 7. So even in this case, right, because we have 1, or 0, 1, 2, 1, 0, 1, 2, 3. So this 7 technically has a score of 3, because the path would be 6, 3, 5. So this is 3, this is 1. So that's 4. So 6, 3, 5, 2, 1, 3. Path length. Is that correct though? The number of nodes minus 1 basically. So 1, 0. 1, 2, 3. But there's 1, 2, 3, 4, 5, 6, 7 nodes between them. But this will only give me 1, 2, 3, or 0, 1, 2, 3, sorry. 0, 1, 0, 1, 2, 3. So this would give me a value of 4, when it should give me a value of what, like 6? So if that's the case, then yeah, okay. So in that case, we actually don't want to subtract the score when we go left, or when we go right. So now I'm thinking whether or not we could actually modify it to go. So now it'd be 1, 2, 3, 4, 5. And this would be 1. But if we take this case, 1, 2, or 2. Oh no, that works. There is no, we don't need to go to the leftmost, we just need to go basically as deep as possible in one direction and as deep as possible in the other direction. Strange. Okay. And now we're getting the wrong answer. Let's see. Start with a simple case. 1. let's see. 1, 2, 2. Right? I'm gonna cut this out for now. I have a feeling that I might need to adjust something here, but left score, right score. I just want to see the left score and right scores of each. 0, 0. So 0, 0 would be here. At this would make it easier to know which part we're at. Zero, 0. And 0, 0 here, which makes sense. At 2, we have 1 and 1, which makes sense. At 3, we have 0, 0. And at 1, we have 2, 1. That makes sense. This is calling pre-order. I forgot about that. And at 1, we have 2 and 1. Which makes sense. Now I'm thinking if I just want to maximize the depth on each side. This might take a little bit longer than I expected. Path may or may not pass through the root. So let me because now I think that when we do the post order, we're actually grabbing these nodes as well. So we're not keeping what we want. Maybe we just keep the right score then. And we just go left, but we don't actually do anything with that. So we just call this pre-order to explore the right side, but we don't actually end up doing anything with it. And that gets us that much, but I have a feeling that this won't quite work with our other example. Something doesn't seem right there, yeah. What if we did something different? So I'm looking at this one. The longest path would be here to here. How do we denote that? This has a path length of 0. Path length 1. 1, 2, 3, 4, 5. So maybe the solution isn't to run 2 traversals, but rather to go in a sort of in a recursive manner, but almost on like a level order. So what I mean is that we start at here, we start at the root, left here and right here, which means that we increase the left score and the right score by 1. Then we call the same method here on the left and the right. So now these have a score of, or actually, well, it'll get proliferated down, so like that. Then you get to these. Because the problem right now is that these are technically overlapping with each other, which is not what we want. And I could imagine a situation where if this branches off and goes all the way like that, then technically the longest path would be to go to that one and not to go here. I'm just confused as to how. I'm gonna give that recursive method a try and we'll see where we go from there. So I'm gonna comment these out for now. We might need them later. But from what I see, maybe we can do something like that where we call it on the left and the right and we add them. So in this case, it'd be 0, call add on here, call add on here. So this would be 0 because it has no children. This would be 1, 2, path length 2, path length 3. Here would be path length 4. 1, 2, 3, 4, 5, 6. So 5 actually. So it would add. If it has a left and right child, it adds 2. So 0, 1, 2, 3, 5. And then 7. No, but we don't take that route. And there's no guarantee on that side. Actually, that works. 1, 2, 3, 4, 5, 6, but 1, 2, 3, 4, 5, 6. No, 9. Yeah, so now this would be the furthest route. 7, 2, 3, 4. Actually, I don't think we even need this. Because 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6, right? So how does this work? Layer 0, layer 1. So here we call the path depth, which is 0, 1, 2. 0, 1, 2. So 2 and 2. 2 and 2 plus 1, so that's 5, right? 1, 2, 3, 4, 5. No, we want to add 2 here. Two here, so that would be 6, right? Because 1, 2, 3, 4, 5, 6. But here we don't want to add 6, we want to add the left side and the right side. But if this goes further, then what if we did a pre-order? And at this point I'm just gonna re-add this. So left score is 0, 1, 2, 3, 4. 5, 6, 7. This is difficult. I don't know why. My brain just doesn't work on binary trees. Definitely need some more practice on this. If we do 4 right here. Anytime we go down a path, it is increasing our score by 1. Anytime we go up on a path, we decrease our score by 1. 2, 3, 4. 2, 3, 4. 1, 2, 3, 4. 3, 2, 1, 2, 3, 4. I think I need to rethink about the way that I'm handling this. Maybe something like think about how we solve this in a way that doesn't do this iterative counting path length stuff. But how? The longest path length is always going to be the longest path length of the left plus the longest path on the right if they exist. If they both exist, then plus 2. But what I want to pass back up, what do I want to pass back up then? Because then the longest path length here that we want to pass back up. So we have a max of 7 here, or 6 rather. Because 1, 2, and 1, 2 plus 2, that's 6. But the path to this root right here is 1, 2, 3, 4 long. So that's plus 2 there. So that's the maximum. This problem is confusing me. Start there. Maybe it is much simpler. Maybe it's just a level order, but you do some weird math. So left and right you add it to a queue, and then so here if you have 2 children you add 2, then you add these to the queue. So max path length is 2. And current 2. Then here would be 3. You could go 1, 2, 3 or 1, 2, 3, right? Then here would be 4. I think I'm gonna take a break from this, think about it some more, and then come back in a bit, because this is gonna take a while. Okay, it's been a couple minutes. I've just been drawing things out on the tablet here. I don't know how well you can see it, but I think my current solution for now is to actually return a class, or rather an object. And that object will hold 2 things. One will be the longest single path, and the second will be the longest path at that node. And the reason why I'm doing that is that we need the single longest path in order for the parent node to calculate whether or not we need to add, or for the parent component to see if there's a better path through them. And we also need the longest path containing that node, in order to know whether or not the better path was already basically found deeper within, so without that node that we're at right now. So I think that's what I'm getting at right now. There's probably a more elegant solution to this, and I'm sure that at some point I'll probably be able to think about it, but currently I have no thoughts, head empty. So path. So we'll use a data class because I don't think there's any necessary reason to use anything else. And we'll have a val single longest path, which is an int, and val longest path, which is also an int. So this is longest path including node, longest path of children, basically. And this should return a path. And I'm gonna need to import Kotlin math max again. And this will take a path. If path is now I'm just thinking this is going to be a very data intensive thing. Not sure if this will even work, because then we need to pass the path within. And we don't particularly care about the path within. And since this is a data class, we can't change the values inside. There's got to be a better solution here. I'm gonna speed this part up, and I'm just gonna mess around and see where I can get with this for now. This is definitely a question that I need to repeat to learn better, but and try to do it without any of the additional standard library stuff for now and see where I just get. Okay, so ultimately I think I decided just to go with a global variable for the longest path. I think it's just the most straightforward approach. I think like for me global variables are a little bit iffy in the sense that I'm not a fan of using them within a solution because it just adds another layer of not self-containing within the actual function. And of course you can say like, okay, like we can say like longest path is equal to 0, right? To reset the state, but again, it's another point of failure here within that's not self-contained within the function. But I think this actually does make a decent amount of sense. So basically what happens here instead is that we go left, we go right, and then here, if the left score is and the right score are both greater than 0, so there's the left and the right, we can then connect the two and add 2 there because of the left and right edges, and check if it's our longer if it's our new longest path. And then if there isn't, so one of these is 0, then we don't want to connect them. We just want to see if there's a longer path. Actually, we don't need to do this at all then. I'm actually gonna just straight up get rid of this and just do an if statement here. So if they're both greater than 0, actually it is possible that a longest path could be without a left and right child. And this would be like in the case of like a linked list. So I'm actually going to leave that there. But in this case, basically, we check if there's a new longest path through either of these ways. And if yes, then we update our longest path. And then otherwise, we just return our single longest path. So what is being returned is always going to be our single longest path through here. So in the case of something like this, right? It'll go 2, 4, 6, 8. And then it'll update the longest path. So now longest path would be 1. Or after we return to, so longest path would still be 0 here. Here, then it would be 1. Here, then it would be 2. Then we go here, here, here. So 0, 1, 2. Now we have a left and a right score here. So now we have our longest path equal to 2 plus 2 plus 2, which is 6. 2 here, 2 here, and then the two edges connecting them. But then what we pass back is actually our maximum of these two. So actually it would pass back, since they're both the same score of 2, this would be updated to 3 because we also add 1. So this would be 3 here. So 1, 2, 3. Or would it be? Do I need to add 1 more? 0, 1, 2, 3. Interesting. I might need to add 1. Let's see what happens when I run it. I haven't ran this code yet. So let's pull up the tree visualizer. So at 8 we have 0, 0. At 6, 1, 0. At 4, 2, 0. 9, 0, 0. That makes sense. 3, 3 at 2, yes. 3, 0, 0. And then at 1 we have 4, 1 because 1, 2, 3, 4, and 1. Right. So then actually we don't need to add these because the 2 is actually inherently already in the within the logic because we're adding 1 each time. Let's pull this up again. So we have 3, 3 here already because it's the pre-order plus 1, so 0, 1, 2, and then plus 1, that's 3 and 3. But what we're passing up is actually 4. And then 4 plus 1 is 5, which is not more. And let's throw in the other example test cases. That seems to do fine. Gonna get rid of the print. So track of longest path globally through a variable, return the longest single path to see if we want to include our parent node for a longer path. So this is an interesting one. I mean, the concept is obviously graphs, but this conclusion is difficult for me to really think of how I would come up with this sort of in a sort of logical manner. The main thing is that really got me is just that we have two things to consider here. One is the single most long path, the single longest path, and that is used in case we want to include our parent node within to see if there's a longer path. And then the second one is the global longest path, the one that we've already seen before. And both of those things are important to consider. However, they're not both something that we can sort of get at the same time. And it doesn't actually work. It doesn't make sense to pass the longest path as a parameter. Though I'm sure that we could find some way to do that. But in this case, it just makes more sense to, within the context of the pre-order traversal, just return our single longest path because that's what's being used as part of the calculations. So let's submit and let's see if there's anything else that we missed and we failed to consider. And maybe there's a way to do this within one traversal. And looking at the speed, maybe there is a way to do this with like 2 pointers within the graph. I'm gonna leave it at this for now. This is definitely a problem that I do want to come back to though, because this screwed me up real bad. So yeah, definitely something to reconsider for a future review session. But other than that, I guess that's it for now. Seems like the solution worked well-ish enough. And I'll see you for the next problem.